Welcome to the Physics Classroom's video tutorial on circular and satellite motion. The topic of this video is satellite motion mathematics, and we want to know what are the important formulas that describe the speed, acceleration, net force, and period of orbiting satellites, and how do you use those equations. Mr. H, let's get started. We'll begin by deriving an orbital speed equation. So I wish you to imagine a satellite that has a mass of m satellite and is orbiting some central body whose mass is m central. The net force acting upon the satellite is given as m times a, or for a circular orbit, m times v squared divided by r. This net force is supplied by the force of gravity, which, according to Newton's law of universal gravitation, is given by the expression big G multiplied by the mass of the central body multiplied by the mass of the satellite and divided by the radius of orbit squared. Now, since the net force is equal to the force of gravity, we can state that these two force expressions are equal to one another, and the result is we have this equation. Now, when I inspect the equation, I notice that the mass of the satellite is on the left and the right side of the equation. So if I divide through by the mass of the satellite, I'll cancel the mass of the satellite from the equation. I also notice that there's a radius of orbit in the denominator on the left side and a radius squared on the right side. So if I multiply both sides of the equation by r, I'll cancel one of the r's from both sides, and the result is I have this equation. Now I'm looking for an orbital speed equation, a v equal equation, and I don't have it yet. I have a v squared equal equation. So I'm going to take the square root of both sides of the equation, which on the left gives me v, and on the right gives me the square root of the universal gravitation constant g multiplied by the mass of the central body divided by the radius of orbit. When we inspect this orbital speed equation, we could draw the conclusion that the orbital speed of a satellite does not depend upon how much mass the satellite has, but instead depends upon two variables, the mass of the object being orbited, the central mass, and the radius of orbit. If we, for a moment, we take this equation, we apply it to a satellite orbiting some planet, maybe it's a moon or a human-made satellite orbiting a planet, we could conclude that if you increase the mass of the planet, you would increase the orbital speed of that satellite. And if you were to increase the orbital radius, you would decrease the orbital speed of that satellite. If we got numerical, we could say if you were to double the central mass, the planet mass, you would cause the orbital speed to increase by a factor of the square root of 2. It would be 1.414 times larger. And tripling the planet mass would cause the orbital speed to be larger by a square root of 3 factor, 1.732 times larger. On the other hand, if you were to double the orbital radius, it would cause the orbital speed to decrease by a factor of 1.414. And if you were to triple the orbital radius, you'd cause the orbital speed to decrease by a factor of 1.732. But if you were to change the satellite's mass in one way or another, it would have absolutely no effect upon the orbital speed. Once in orbit, the only force that acts upon an orbiting satellite is the force of gravity, and as such, the acceleration and net force of an orbiting satellite is simply the acceleration caused by gravity, g, and the force of gravity, F grav, which according to Newton's law of universal gravitation is given by these equations, where g, big G, is the universal gravitation constant, the value of which is shown, and r is the radius of orbit. But since satellites are orbiting in what is nearly a circular orbit, we could also use circular motion equations to describe the velocity, acceleration, and net force. So v is equal to 2 pi r divided by the period, and the acceleration is v squared divided by r, or 4 pi squared r divided by t squared. For net force, you would state that it's m times a, or for moving in circles, it's m times v squared divided by r, or m times 4 pi squared r divided by t squared. Satellite motion is an example of periodic motion. That is, the satellite orbits the central body over and over again in a repeated and regular manner. In fact, the orbits are so regular it's almost as though you could keep time by it. The time it takes for a satellite to orbit the central body is known as the period and represented by the symbol t. This period is independent of the mass of the satellite and only dependent upon the mass of the central body and the radius of orbit. The equation is shown here. In order to derive a t== equation from this equation, we would have to multiply both sides of the equation by r³ and then take the square root of each side. We would end up with this result, which is such a cool equation that I actually had it tattooed just above my belly button a few years back, and I'd like to show it to you.
Mr. H, no, don't do it, don't do it.
Fortunately, circular motion equations can also be used to calculate the orbital period, the best one of which is 2 pi times the orbital radius divided by v, the orbital speed. The table here summarizes the different equations that you will be using to calculate the orbital period, orbital speed, acceleration, and net force. Exactly which equation you use is dependent upon what you know and what you're looking for. It's best to practice the habits of a good problem solver. Read the problem carefully. Write down what you know, expressed in symbol form. Write down what you're looking for, again, expressed as a symbol. Then look for the formulas that contain those symbols in order to determine which one you use. In my first example problem, a satellite is orbiting the Earth at a height of 100 kilometers, and I want to determine the orbital speed, acceleration, and orbital period of the satellite. I know the mass of the Earth and the radius of the Earth. My first step in the solution is to determine the radius of orbit, and that's not equal to the radius of the Earth, since the satellite is not orbiting on the Earth's surface, but rather 100 kilometers above its surface. So I need to take the radius of the Earth and add the height above the Earth that the satellite is. To do so, I need to first take 100 kilometers and convert it to meters, 1.0 times 10 to the 5th meters, and then add that on to the radius of the Earth. Once I'm done, I have the radius of the orbit, and that's the r value that's used in most of the circular motion and satellite motion equations. Now to calculate the speed, I could use just about any equation, but the one that I'm going to use is v equal the square root of big G times the mass of the central body, which is the Earth's mass, divided by the radius of the orbit. When I take my values for m and r and g and substitute it into the equation, I get approximately 7,850 meters per second. Now I'm going to calculate the acceleration using the circular motion equation, a equal v squared over r. I've just calculated v. I use the number on my calculator, square it, and I divide it by what I've calculated as the radius of orbit. And when I'm done, I get an acceleration value of 9.52 meters per second squared. Now I'm going to calculate the orbital period using a circular motion equation of v equal 2 pi r over t. But I'm going to rearrange it to the form of t equal 2 pi r over v, take my v value and my r value, substitute it in, and I get the value for the orbital period. In my second example problem, I'm given the orbital period of the Moon in days and in seconds, and the mass of the central body, the mass of the Earth, and I wish to calculate the orbital radius of the Moon and the orbital speed of the Moon. To calculate the orbital radius, I need an equation that has in it radius, period, and mass of the central body. And that would be this That would just be this equation right here. And in order to calculate the radius from this equation, I have some algebra to do. I need to square both sides of the equation to get rid of the radical sign, multiply both sides of the equation by r cubed to get it out of the denominator, and divide each side of the equation by t squared. And when I'm done, I have this result. Now I can substitute in known values of the mass of the Earth and the radius and the period of orbit, and I can calculate the r cubed value for the orbit of the Moon around the Earth. Once I get r cubed, it's not the radius. I need to take the cube root of that, and that gives me the radius of the Moon's orbit. Now, in the second part of the problem, I have to calculate the orbital speed, and there's a couple of ways to do that. The easiest one would probably be to go v equal 2 pi r divided by t, but that would be way too easy, so instead I've chosen to use the equation v equals square root of g times the mass of the Earth divided by the orbital radius. When I substitute in my values to calculate the orbital speed, my calculator tells me that it's 1,020 meters per second. In the third and final example, I'm given the orbital period and orbital radius of one of the moons of Saturn, and I wish to calculate the mass of Saturn. In this situation, the Moon is actually a satellite and the central body is Saturn, and I need an equation that relates mass to orbital period and orbital radius. So I need to use this equation right here in order to calculate the mass of Saturn, but first it needs to be rearranged so that I can solve for mass. There's a couple couple of steps of algebra that would look something like this, and then once done, I would substitute values of radius and period into the equation, and I can have the mass of Saturn. And it would have been a lot easier to Google it, but where's the fun in that? It's at this time in every video that I like to help you out with an action plan, a series of next steps for making the learning stick. But before I help you out, could you help us out by giving us a like, subscribing to the channel, or leaving a question or comment in the comment section below. Now for your action plan. Here are 3 resources that you'll find on our website, and I've left links to each of them in the description section of this video. You have a Minds on Physics mission on satellite motion, a load of problems from our calculator pad section with problems, answers, and audio-guided solutions, and a written tutorial page. Whatever you do, I wish you the best of luck. I'm Mr. H, and I thank you for watching.